Good afternoon. I am Dr. Abhishek Das, Assistant Professor, Department of ECE, Haldia Institute of Technology. Today we will discuss the theory of antenna array. So, in the lecture, what are the content of the lecture? First, we discuss the antenna array introduction. Second, we discuss the two element array. Next, we discuss the array factor. Next, discuss the broadside and end fire array. After that, we discuss what are the linear antenna array and the effect of number of elements, number of spacing and the phase difference in the array factor. If we change or increase the number of element, what will be the effect in the array factor? If we change the spacing between the two elements and if we change the phase difference or phase excitation on each element of the array, then what will be the effect on the radiation, that we will discuss in this slide. In the next slide, we discuss the what is antenna array. So, antenna array, as a definition, we know antenna array are a configuration of multiple radiating elements in a geometrical order. Antenna array are an efficient way to freely change the pattern of an antenna, making it more directive and therefore increasing the gain. Okay, electronically adjusting the excitation of individual elements leads to a phased array, which enables greater degree of freedom. Okay, this is the definition of antenna array. So, why we use the antenna array? That is the when a number of antenna are placed together, it forms the array. Look here, that is the number of, it is a picture of the planar antenna array. Here it is the one antenna, this one is the second antenna, this one is the third antenna, fourth antenna. Similarly, there are several number of antenna are arranged in a particular geometrical configuration. So look, it is the planar antenna and it is in the square shape. Okay. Similarly, this is the also one picture of the antenna array where a number of antenna are placed together in a geometrical configuration and it forms the circular antenna array. Okay. In the next slide, we discuss the antenna array. In an array of identical radiating elements, there are at least 5 factors that can be controlled to shape the overall pattern. So, the overall radiation pattern of an antenna array can be controlled by 5 factors. And what are the 5 factors? First is the geometrical configuration of the array. So, what are the geometrical configuration of the array? This one is the figure 1. So, we can see there are also number of antenna elements are placed together and it forms an antenna array. But here it is a planar antenna array where look, this one is the first column, this one is the second column, this one is the third column, this one is the fourth column. Similarly, there are several rows and several columns is there and it forms a rectangular array. But in the figure 2, you can find that is there are also several number of antenna are placed together, but its geometrical configuration looks like a circle and it forms a circular array, right? So, antenna array, that is the first factor or first important factor is the geometrical configuration of the array. If you change the geometrical configuration of the array, that is the total radiation pattern of the array is also changes. So, what are the general geometrical configuration of the array? First one is the linear array or circular array or rectangular array or elliptical array, different geometrical configuration. In such configuration, number of array and number of antenna elements are placed together as a linear element or as a circular element or as a rectangular element or elliptical element, etc. And it forms a geometrical configuration. Second one is the relative distance between the element. So look here, it is also forms a linear array, as because this one is the antenna 1, this one antenna 2, this one is the antenna 3 are placed together and it forms a linear antenna array. And the second factor is the relative distance. So if this one is the antenna 1, this one is the antenna 2, so what is the distance between these two elements? This is the, we generally represent with the term d. So depends on the d, that is the antenna radiation pattern is also changes. In the next slide we discuss that is the what are the effect of the d in the array factor as well as the radiation pattern, we will discuss later. Okay, next is the third point is the excitation amplitude of the individual element. So in the array, if we consider the linear antenna array, if this one is the antenna 1, this one is the antenna 2, this one is the antenna 3. So for each antenna we need to excite or we have to give the feed current. If we change the amount of this feed current, then also we find that is the radiation pattern is changes. Right? Next is the phase of the individual element. So if you consider this one is the linear antenna array, so in this array this one is the antenna 1, this one antenna 2 and this one is the antenna 3, and we give the phase excitation of each individual antenna element. Okay, so if we change the phase excitation of each antenna, then also we can find that is the radiation pattern is also changes, right? And the fifth one is the relative pattern of individual element. So antenna array can be formed with different type of antenna. It may be dipole antenna, it may be horn antenna, it may be dish antenna, or it may be patch antenna. With the different antenna have its own radiation pattern. So if we change the individual element, then also we can find that is the radiation, total radiation pattern of the array will changes. So what are the 5 factors of array radiation? Is the geometrical configuration of the array. This one is the first one. Second one is the relative distance between the each array element. Third one is the excitation amplitude of each element of the array. Next is the phase excitation of each element. Okay, and last and the fifth one is the relative pattern of each individual antenna. So if you change, that is the from the dipole antenna to monopole antenna or microstrip patch antenna, each individual antenna has its own element pattern. Okay, if you change the antenna each individual element, then also we can find that is the radiation pattern changes. So here you can find in the figure there are the 3 number of elements. Antenna elements are arranged in a linear fashion, and the radiation pattern of the antenna array is result of interference between the individual antenna radiation pattern. In the next slide we discuss the 2 element array. Here the 2 dipoles are placed along the z axis. The total field radiated, assuming there are the no mutual coupling between them, is equal to the sum of the 2 elements in the yz plane. So total radiation will be equal to what? E1 and E2. E1 the radiation generated due to the antenna 1, and the E2 is the radiation generated due to the antenna 2. So total E is equal to what? E is equal to E naught e to the power minus j beta r1 plus E naught e to the power minus j beta r2. So what is this R and R2? If you see, this one is the figure, far field figure. R1 is equal to what? R1 is equal to this one, and the R2 is equal to this one. So this one is the total radiation of the 2 element array, right? In the next slide we discuss the what is array factor. What is array factor? antenna array consisting of a collection of identical elements are usually characterized in terms of their array factor. The array factor of any given array of identical antenna elements is product of the number of elements, the relative input signals of various elements, and the geometrical arrangement of the elements. So look in the figure, here is the electric field of the patch antenna. This figure is the electric field of the patch antenna. Okay, and this one is the array factor. So the total radiation will be equal to what? Total radiation E total is equal to the individual element multiplication with the array factor. If we multiply the array factor with the pattern of each individual element, then we will get the total radiation. So here it is written, the total electric field E total radiated from an antenna array is equal to the product of the array factor AF and the electric radiation pattern of a single antenna element located at the origin. Okay, and this is called the pattern multiplication. This is called the pattern multiplication. If we multiply, that is the element pattern of each single antenna element with the array factor, then we will get the total electric field radiated from the antenna. And here in the figure we can discuss here that this is the electric field of the patch antenna. It is multiplied with the array factor of the two element array, and after that what the radiation pattern we will get here. This one is the total radiation pattern. Okay, this one is the array factor. Next we discuss the radiation example. Radiation example means what? So look here, the two figure is there. One is the single isotropic radiator, and here is the array of two isotropic radiator placed, and the distance between the two radiator is the lambda by 2. So this is the figure. We can see that is the interference pattern of the total radiated field constitute the array factor for each array. So here this one for the one single isotropic radiator, what is the radiated field from the single isotropic element, and this one is the when the two isotropic elements are placed together, it forms the two element array, and therefore we can find due to the interference, that is the radiation pattern is also changes, right? So this is the effect of the when we increase the number of element, then also we can find what are the changes in the radiation. So this one is the linear array. Here the uniform amplitude and the uniform spacing. So this is the figure. Here the antenna 1, this one is the antenna 2, this one is the antenna 3, this one is the antenna 4, similarly this one is the 5. So here look, this each antenna is placed linearly and it forms the linear antenna array. Okay, so this is the one example of the linear antenna array. And uniform array is an array of elements all with the identical magnitude and each with a progressive phase. So what is the definition of the uniform array? Uniform array means the where each antenna elements have the identical magnitude. So this one is the example of the linear array of uniform amplitude and the spacing. So it forms the array. So look here, there are several number of antenna 1, antenna 2, this one is the antenna 3, 4, 5, 6, 7, 8. So there are n number of antenna are placed. Therefore what happen, each antenna will radiate. So when the radiation is when each antenna will radiate, that is the each pattern will interfere with the other, and how it radiate. So here it is the figure when there are n number of antenna forms one linear antenna array and how the radiation occurs. This figure depicts that one only. Okay, next is the n isotropic point source of equal amplitude and spacing. When n number of isotropic antenna, this one is the antenna 1, this one is the 2, this one 3, 4, 5. Similarly, if there are the n number of antenna elements are placed, and the distance between the two antenna is the d when these are placed. Then what is the total radiation? Total radiation is this one. Here we give the formula. This one we can find the total E is equal to 1 minus e to the power j sigma by 1 minus e to the power j sigma. So from that we get the total radiation. Okay, so this one for the n isotropic source of equal amplitude and spacing. Next we discuss the array. There are mainly two types of arrays there. One is called the broadside array, another is the end fire array. So first we discuss the broadside array. What is the broadside array? In many applications it is desirable to have the maximum radiation pattern of an array directed normal to the axis of the array, that is theta is 90 degree. To optimize this design, both the maximum of the single elements and the array factor should be both directed from theta equal to 90 degree. So this is the one figure of the broadside array. Broadside array means the radiation, if this one is the axis, so radiation, maximum radiation occurs at the 90 degree. So if this one is the axis, so maximum radiation occur at the 90 degree. So here it is told in the definition of the broadside array. Here it is told that is the to have the maximum radiation of an array directed normal to the axis of the array. So if this one is the array means that this one is the antenna 1, this one antenna 2, this one antenna 3, there is the 4. So this one is the axis of the antenna and the maximum radiation is normal. Normal means that is the 90 degree from the axis, and if the radiation is such type of radiation is known as the broadside array. This such type of radiation is known as the broadside array. In the next slide we discuss the ordinary end fire array. So what is the end fire array? Instead of having the maximum radiation broadside to the axis of the array, it may be desirable to direct it along the axis of the array. And if we want the radiation along the axis of the array, so look, this one is the array. Here the antenna number 1, this one 2, this one 3, this one is the 4. So if we want the radiation along the axis of the array, then it forms the end fire array. And if we want the radiation along the normal of the axis of the array, it forms the broadside array. So there are mainly two types of arrays there. One is known as the broadside array, another is the end fire array. If we want the radiation pattern normal to the axis of the array, it is known as broadside array, and if we want the radiation along the axis of the array, it forms the end fire array. So this one is the figure for the end fire array. Okay. In the next slide we discuss the array factor of uniform antenna array. From the equation of the array factor we can understand that the array factor is a function of array setup, the number of elements that forms the array. Okay. Next is the spacing between the two elements and the phase difference between the neighboring elements. That is the in the previous slide we already discussed. So for the array factor there are mainly 5 conditions. So depends on that 5 condition, radiation pattern change. First one is the excitation amplitude of each element of the array. Okay. Next is the after the excitation amplitude, spacing between the two elements. Third one is the what is the phase on each element of the array. And the fifth one is the what is the fifth one is the what type of antenna, single antenna element is used. Depends on that total radiation pattern of the array changes. Okay. So this one is the array factor. The array factor can be plotted in Cartesian or polar plot. So here this one is the Cartesian plot and this one is the polar plot for the array factor. In the next slide we discuss the array factor of uniform array. So this one is the linear uniform array where number of elements, if this one is the antenna 1, this one is the 2, this one is the 3, and this one is the 4. So number of antenna, 4 number of antenna are placed linearly. So it is the one example of the linear array. So array factor of uniform array factor. So for an array where each element is driven with the same current magnitude, the strength of the radiation will naturally increase as the number of radiating elements increases. However, this does not necessarily reflect a system improvement, since the higher power output is proportional to a higher power input. In order to avoid the conflicting this effect with an actual gain improvement, the array factor is often reported as normalized value. Okay, a linear uniform array can steer the radiation in the direction of the array. For instance, an array of isotropic radiator arranged along the z-axis may be used to steer the beam in the theta direction, angle from the z direction. So for the we can change the radiation pattern. We can change the radiation pattern of the linear antenna array in any angle. That is, we can change the theta direction. If we change the phase excitation of the each element of the antenna, then the radiation pattern will steer to at any particular angle. So we can steer the beam by changing the phase excitation of each element. Okay. In the next slide, we discuss the array factor of uniform antenna array and its effects on the number of elements. And on the when we discuss the content of our lecture, so we discuss, that is the for the array factor, the radiation pattern of array depends on the number of the elements. Okay, so if we change or increase the number of elements, or if we decrease the number of elements, how it will change the array factor as well as the radiation pattern of the array, that we will discuss. So in this slide, for an array with a fixed spatial separation between the elements, increasing the number of elements similarly results in compression of the radiation pattern. Look here in the figure, this one is the antenna 1, this one is the element 2, there is the up to n number of antenna elements are placed, and here what is the distance between the two elements is the d. So therefore it forms the uniform linear antenna array, as because difference or distance between the two each antenna element is the d and it is fixed, therefore it forms the uniform linear antenna array. Now in this uniform linear antenna array, if we increase the number of element, how the radiation pattern changes, that we will discuss here. So this one is the figure 1. We can find here the total number of element is the n is equal to 2. N is equal to 2. This one is the radiation pattern when there are 2 number of linear antenna elements are present. So here look the radiation pattern change. If we increase the number of element, here n is equal to 3. Similarly, if we increase the number of element, n is equal to 4. Here the n is equal to 5, n is equal to 6, n is equal to 7. We can find the radiation pattern of the antenna array is changes. So if we increase the number of element, we can find, that is the radiation pattern of the antenna array, it becomes more directive. It becomes more directive. Understand? So if we increase the number of array elements, then that is the pattern become more directive. So in the next slide, we discuss the array factor of uniform antenna array, and here we discuss the effect of element spacing. If we increase or decrease the spacing between the two elements, what will be the changes, that we will discuss in this slide. The spatial separation between the elements in an array increase the apparent electrical size of the effective radiator. So if we increase the distance between the two elements, if this one is the antenna 1, this one is the antenna 2, so and the distance between the two elements is the d, if we increase the element, then what happen? That is the total radiator size becomes larger. But if we change or decrease the distance between the two elements, then what happen? That is the radiator size become smaller. So this increase in electrical size enables a compression of the radiation pattern in the dimension of the array. So for a fixed number of element, increasing the separation d between the element increase the observed compression of the primary lobes of the radiation pattern. So here we discuss that is the what is the effect of the element spacing. Element spacing means that here we consider a linear antenna array where the number of elements of the array is fixed, but here we only change the distance between the two elements, that is we change the d. So what will be the effect on the array factor, that we will discuss. So this one is the figure 1. Here for the array factor d is equal to, we consider d is equal to 0.2 lambda, and here the array factor for d is equal to 0.3 lambda, here d is equal to for 0.4 lambda, here d is equal to 0.5 lambda. So for different spacing between the two elements for a particular or fixed number of antenna, what will be the changes? We can see that is the radiation pattern changes if we, that is the decrease the spacing between the two elements. Okay. As shown below, the two elements array has progressively more compressed radiation as the two elements moves further apart. So however d increases beyond 0.5, a secondary set of lobes appears pointing in the dimension of the array. Here we discuss here, this one is the for the figure 1, this one is the for the figure 2, figure 3, this one is the figure 4. If we increase the distance, we can increase the distance between the two elements, we can find that is the radiation pattern become more compressive. Radiation pattern, here it is written progressively more compressed radiation as the two elements move further apart. Okay. In the next slide, we discuss the array factor of uniform antenna array, and here we discuss in this slide the effect of phase difference between the element. So here also we consider one linear antenna array. Here this one is the antenna 1, this one is the antenna 2, this one is the antenna 3, 4, 5. So here what we do, that is the distance between the two element we keep it fixed and the value is the d, and here the number of total antenna elements in the array that also fixed, but here what we change the only the phase excitation on each individual element. So what is the changes? So that change we discuss in this slide. So look here, it is written another valuable control variable at our disposal is the linearly stepped phase difference. This one is the psi between the neighboring elements in the array. An array that utilizes such a variation in the phase of the driven signal is called the phased array and can be used to dynamically steer the beam without physically rearranging the element. So here psi is equal to, we consider it is 0 degree, and here psi 0 means the phase angle, we consider it is 30 degree, and here the phi 0 means the phase angle, it is the 60 degree, and here the phi 0 is equal to 90 degree. If we change the phase angle, then also we can see that is the radiation pattern of the antenna array changes, right? So here we discuss in the figure 1, this one is the figure 1, this one figure 2, figure 3, and this one is the figure 4. If we changes the phase difference, keeping the total number of elements of the array fixed and the distance between the two elements is fixed, we only change the phase difference, then also we can see that is the radiation pattern of the array changes. Okay. So that's all for today. In the next slide, we discuss how that is the radiation of the antenna array changes with each element Each element means that one array forms with a total n number of array elements. If we change the current excitation of each element or distance between the each element and the phase excitation of each element, that is the vary in the radiation pattern that we already discussed. But in the next lecture we discuss, that is if we can apply some optimization technique by which we can get an optimal radiation pattern by changing the phase excitation or the spacing between the two array element changes, or the current amplitude of the each element if we change by changing the current excitation amplitude weight, or changing the spacing between the two elements, or by changing the phase excitation of the each element, how the radiation pattern changes optimally, that we discuss in the next lecture. Thank you.